distribution system through smart metering scheme, grid integration of distribution generation, and electrical vehicles for performance enhancement of network, ancillary support and demand side management, study of impact of large penetration of renewable energy resources such as wind and photovoltaic generation in power grid. His current research interests should include voltage stability studies, application of FEX controller, power quality, wide area monitoring system, and smart grid. Professor Verma has reviewed the books Electrical Circuits Analysis and Network Theory, written by Professor Shauri Chatterjee, and IT Delhi, and Professor and Power System 1, written by Dr. Suresh Mikhili, Dr. NIT Goa. Sir, we are truly honored to have you with us today. With that, I now invite Mr. MK Verma to kindly take over the session from here. Sir, take the time. Is all yours. Thank you.
Okay, thank you, Khushbu. Am I audible to everybody? Am I
Yes, sir.
audible?
Yes, sir. You are
Okay,
audible. Please.
okay. Yeah, is my screen coming? Is my
Yes, sir.
screen visible?
Yes, sir. It
Okay.
is visible.
So, okay. So, title of my presentation is Towards Resilient Smart Grid. So, you know what is a smart person? A person which is able to take decisions in intelligent manner. So, similarly, our grid is becoming smart. So, it has intelligent control, unlike the classical grid, conventional grid, which was having the conventional controls. And we want to make this grid resilient. That is, the grid should be able to recover quickly following disturbance. So this will be the outline of my presentation. First, I will give the concept of macro, nano, and smart grid. And then I will talk about what is meaning of resiliency and how then resiliency of the grid can be enhanced. And then what role the wide area monitoring system can do in real time of monitoring of the system to enhance the grid resiliency. Then the grid has smartness of grid will be incomplete because without making distribution system smart. So I will talk about the smart distribution system with its important features and how we can monitor and control and protect these smart distribution networks, what strategies are to be adopted. So first let us start with the basic of power grid. Now, what is power grid? It is the interconnected power network, and to this grid, all the generators can inject power. So unlike radial distribution network, where the if some part of the network is disconnected due to some outage, consumers is unable to get this power. But here, in case of grid, even if some part of the network goes, still the consumers can get power through this grid system. So it is feasible to send power from any part of the network to other part of the network. And this grid maintains a constant frequency under steady state conditions. And these frequency variations must be beyond acceptable limits. If it is not so, then it may threaten the partial or complete frequency failure of the grid. Apart from frequency control, it requires a quite large number of other controls like maintaining voltage, the line flows are to be within the limits, and that there are other controls, reactive powers of the flows, loss is to be minimum, voltage profile is to be improved to be in the best possible manner. Now, once we have interconnected system, there are a lot of controls that are required to maintain its proper functioning. So there must be proper coordination among controls. Otherwise, if there is improper control, it may, instead of helping the grid, it may lead to outages. And it may result in even cascaded outages, resulting in failure of the grid. So a great example is of grid failure resulted in July 30th and 31st, and that happened due to relay maloperations. So we have protective system, the different relays, but if there is no proper coordination among them, that may be create problem. So there must be proper synchronization of all the equipments, and they must be coordinating with respect to each other. So the grid has the advantage of supplying power to any part of the network from any remote area. You can send power, but it must be properly controlled. Else, it may cause the failure or disruption of supply even for hours. So presently we have the national grid. Our country is divided into 5 regional grids. One is northern grid with headquarters at New Delhi. It covers the 9 states and Union territory of Uttar Pradesh, Uttarakhand, New Delhi, Rajasthan, Haryana, Punjab, Himachal Pradesh, Chandigarh, J&K, Ladakh. Southern grid consists of 5 southern states and the Union territory of Puducherry. The western grid consists of the western states, the Gujarat, Madhya Pradesh, Chhattisgarh, Maharashtra, and Goa. Eastern grid consists of the Bihar, Jharkhand, Bengal, Odisha, and Sikkim. And northeastern grid consists of all 7 sister states of the India. So early prior to 61, the state electricity boards were managing their own networks. There was no synchronization of the power network of the country. So the advantage that it has its own advantage, system is small, but the disadvantage is somewhere there is a requirement of have a scarcity of power. We are unable to send the power. So in 61, prior to 61, the grids were not synchronized, and we have state electricity boards. And 61, the five regional grids were formed that I talked in the previous slide. Then, but they were operating in isolation. Then in October 91, the northeastern and eastern grids were synchronized. Then western grid was synchronized in March 2003, and northern grid was synchronized in August 2006, and finally southern grid was synchronized on December 31st, 2013, through the connection of the 765 kV Raipur Solapur transmission line. So today we have one nation, one grid, and our national grid is the largest among the world and has a total installed capacity of 496 gigawatt at present. So advantage, apart from this, we are also transmitting power, sending power to Nepal and Bangladesh. Now, what is the whatever national grid we have, the large grid, it is the macro grid or large grid, which has it is a large interconnected power network like our national grid. The micro grid is small grid. On a small scale in the local area, there may be some distributed generations, and that can locally supply to some area. Say, for example, your Allahabad city or so, or your campus, so, with means of renewable energy resources. So this is called microgrid. The microgrid can operate in isolation or it may supply to the main grid, depending upon requirement and depending upon availability of power. A nanogrid is further small grid, very small in size. For example, say we have apartment and we are putting solar panel on the rooftop and it meets locally the demand of the consumers in that building. So that is the nanogrid. Similar to microgrid, nanogrid can also operate in islanding mode or it may be connected to the main grid. Now, what is smart grid? Smart grid has intelligent controls for its operation and it has bidirectional flow of power. So earlier we had the monodirectional flow of power, that is from the supply utilities to consumers. Now consumers can also inject power and they can also earn money. They can have the relaxation in tariff. So they can produce electricity, they can also inject. Say, for example, people are putting solar panels in their houses and they can, in the off-peak hours, they can inject the power. So consumer has become prosumer. Prosumer means producer plus consumer. So they are able to produce as well as consume. Smart grid encourages the environment-friendly renewable sources of energies, which can be installed in the form of distributed generations a number of places. And you may have small-scale generation that can meet local requirements. And these are not creating pollution also. So environment-friendly. Informations also flow in the bidirectional fashion in the smart grid. So you may have from consumer to supplier and supplier to consumer, a voltage, current, power, frequency, all these can be transmitted from the remote location to control center, and control center there are application softwares, and from there where these decisions are taken, and finally again that the decisions can be intimated to operators at the remote location. So informations can also flow in bidirectional manner. Similarly, in the consumer side, you can have smart metering scheme through which the data can be transmitted in the bidirectional fashion. And the whole system can be monitored through wide area monitoring system using the synchrophasor technology by means of phasor measurement units. Now, what is the difference between resiliency, security, and reliability of the grid? So, grid resiliency is its ability of the grid to recover quickly under extreme disturbances. So, these extreme disturbances include the natural disaster, extreme weather conditions, and cyber attack. The security is ability to survive in disturbances. And the reliability is ability to maintain continuity of supply with minimum interruptions. So, if there is some disturbance, and under disturbance also, under severe disturbance also, system remains normal. So all load constants and operating constants are satisfied. We tell the system is secure. Now, if failure occurs, then how quickly system recovers from the failure? That is the resiliency. And reliability is the system is reliable if it has minimum number of failures. So if failure occurs, then how quickly you recover? That is resiliency. So if failure is less, number of failures less, it is more reliable. So it means suppose somebody has got disease, so how quickly he recovers from the disease, that is resiliency. But how many diseases somebody gets. If somebody gets less number of diseases, so we can tell that is more reliable against this suffering from diseases. And what is security? Even if some disease occurs, all organs function normally. So that is the security. Now, how can you enhance the resiliency of the grid? There must be some sufficient backup generations to meet demand under contingency. Some outage occurs, and suppose we are unable to supply from the routine generators which are supplying this area. You should have some backup generation, maybe in the form of decentralized generation and distributed generation that can locally supply that part of the network so that system can again recover. So there should be sufficient backup generations. You can have the renewable energy resources installed at the critical locations, distributed generations, energy storage systems can be used in the hour of need. You can have fax controllers and HVDC line. The fax controller can quickly control the power flow through the lines and the uh, uh, we can put it in critical locations, in critical lines and critical buses, so that if some failure occurs, it can control the system and again the system can be recovered. HVDC line has infinite stability limit, so it is more stable compared to AC system. And also we have controls on the both side converter through which you can have the quick recovery of the system. The system we can design the system robust against extreme weather conditions. Suppose you are designing conductors, we are putting line, poles, etc. So towers, so they should be robust and they should be able to bear the extreme weather conditions and natural disaster. There must be proper coordination between protection equipment. So we have seen the example of July 30th and 31st, 2012 blackout, where almost whole part of the country was disturbed for hours. And if there were proper coordination between the relays, you could have avoided the amount of interruption. You should have real-time monitoring of system through SCADA environments. We can regularly monitor the health of the system so that we can see where is the problem, and if some problem occurs, if some disruption occurs, then how we can recover it immediately within short duration. AI in data analytics can be used in real-time fault detection and prediction. So we can detect where is the fault, and accordingly we can adopt different measures to clear the fault and recover back the system. Currently, since smart grid is encouraging the bidirectional flow of information, there is quite chance of the cyber attacks. So our data transmitters is to be having enough cyber security so that we can minimize the chances of attack. So that can make it more resilient. Reconfiguration of network, we can through reconfiguration, we can reduce power loss, we can improve voltage profile, and if there is some outage somewhere, we can send power through other route to the consumers. So that can also help in the resilient operation of the grid. Now I will talk about real-time monitoring of system in smart grid through wide area monitoring system. Now, what issues are to be addressed in the wide area monitoring system? The conventional methods of monitoring are not much helpful. Earlier, something happened, there was phone calls from the operators to somebody in the control center that was not cleared. That the clearing of the faults was taking time because there was also sometimes miscommunication or something like this. Now, in the smart grid architecture, we can monitor the health of the system through this SCADA and wide area monitoring system. So we have PMUs at the different locations. We can have the measurement of complete voltage, current, phases, and frequency, and through which from the real-time data we can have the analysis and we can analyze the system, and accordingly we can see where there is some issue, and accordingly we can plan the controls. So we need the real-time monitoring of the system in a smart fashion to to enhance its resiliency. The restructuring of power system creates new problems because in case of restructure extreme market, mostly the generating companies are many, distribution companies are there, but they are using same transmission corridor, and in the uh, nobody will bother about the security of the grid, but they will try to pull the maximum power from the route uh, to get, and the generators will also try to send the power to earn money. But in that process, some of the lines may get congested. And if their line is congested, it may also lead to the outage of the line, and that may create congestion in other lines, and that may lead to cascaded tripping of the line. So, in order to enhance resiliency, the proper congestion management required so that even some line trips, it should not spread over other lines, and we can quickly recover the system. The sufficient ATC is required because if you have sufficient available transmission capability, then even under stressed condition, we have enough reserve that can be used to supply the system, and that will make the system more resilient in the competitive market environment. Introduction of renewable energy sources puts the new constant because renewable energy sources you can generate locally in the form of distributed generations, but there are a lot of uncertainties in these. For example, if you have wind generations, you don't know when the what will be the speed of wind at different times. It varies with season also. Similarly, if you have the photovoltaics. Um, Also, it depends upon the sunlight available. So all these sources have got the uncertainties associated with it. So we have to handle those things to maintain stability so that we can improve any resiliency of the grid in the smart grid architecture. Now, with the advent of phasor measurement units, I have already told that it is possible to monitor the health of the system through time-stamped measurements via GPS. These measurements are synchronized, and we perform measurements with the accuracy of microseconds. And these PMUs are able to have the fast estimation of voltage and current phases using discrete Fourier transform. At PMUs, you cannot place every locations. You should, with the minimum number of locations placed, you should be able to completely observe the system. Completely observe the system means we can completely monitor the whole system. Even with the loss of 1 or 2 PMU, you should be able to monitor the system. Now, the PMUs should be tuned with the facts parameters because fact parameters are controller which are helpful in controlling the system. So these fact parameters should be tuned to PMUs measurements for real-time control of the system. So facts are also costly. You cannot put everywhere. So we need optimal placement of fact controllers to minimize chances of failure, and also placement of multiple fact controllers can be planned. And I told that the PMUs can be synchronized to the fax parameters, and the line conjunctions and ATC of real-time systems are to be monitored fast through PMU measurements. Now, this is one paper on optimal placement of PMUs in power system network for voltage stability estimation under contingency. So if system is more voltage secure, resiliency of the grid can be enhanced. So this is based on voltage stability criteria. The PMUs has been placed at certain locations, and the work done by one of my PhD student, and the paper was presented in the SERA 2017. The objective of the work was to consider the optimal placement of PMUs, considering voltage stability criteria, voltage stability under critical contingencies, and to make the network completely observable with optimally placed PMU, even in case of critical contingencies, and to monitor the voltage stability of real-time system with these optimally placed PMUs. So for criteria for identifying critical contingency was based on the voltage stability margin, because this was the offline strategy. So accuracy was considered in this uh, planning. For PMU placement is offline strategy. So accuracy can be decided based on voltage stability margin. So contingency which were having the lower voltage stability margin, they were considered more severe contingencies. And then for severe contingencies, the PMU placement strategy was adopted. And the load were varied as per this fashion. The lambda is the loading factor, and pattern of load increase was changed by having different values of K for reactive variable power variation. K varies from zero point 0.2 to 1.2. And this was the PMU placement was done by a binary integer linear programming for system interrupt case and critical contingency cases. And this was the X was PMU placement was done by this the considering the decision variable xi, 1 where the bus where PMU is placed, 0 if the bus is PMU is not placed. These rules were adopted for minimizing the number of PMUs because if PMU is placed a certain bus, it can measure the voltage, current, and frequency at that bus. And if bus is connected to other bus, then by Ohm's law, you can calculate voltage drop in that line that is connected to other bus. So no need of putting PMU at other bus. Now, if the voltage phases at both ends are known, the branch current can be calculated. And if the zero injection bus, then we can calculate the currents in different branches connected to it by KCL. So that can minimize the number of PMUs to be placed. So this PMU placement was considered based on total observability index. The bus observability index was defined as the number of buses connected to a particular bus. So if you put PMU at any particular bus, and if this bus is connected to other buses, it can we can calculate voltage other buses. So you cannot put, we no need of putting PMU at those buses. And total observability index is the summation of bus observability index. And this total observability index should be high enough so that even if the few PMUs are lost, still we should be able to observe the system, health of the system. So this was tested, the effectiveness of PMU placement was tested on some case studies was done. And the critical buses were obtained based on sensitivity dV by d lambda calculated near nose point. So these are some results. Then I will talk about smart distribution system. I told that the grid, the completeness of the grid being smart will be incomplete if distribution sector is left. So we need not only the generation and transmission to be smart, but the distribution system also need to be smart. So what are the features of smart distribution system? The smart distribution system has the bidirectional flow of electricity informations between consumers and suppliers. And there's automated online monitoring control of distribution network for smart metering scheme. So smart meters are put at consumer premises, which can interact with the control center. It can send the data, and the control center takes decision, and accordingly, the consumer can be also intimated about different billings, etc. Also, and they can also be know the consumers can also know whether how much there is consumption, and they can play an important role in demand side management. They can divert their load from the peak hours to off peak hours. So consumers also play an active role, and consumers can also inject power to the grid. So they become prosumer. They can also produce electricity. A smart distribution system includes distributed generations, microgrid, electric vehicles, energy storage system, and there's complete automation of distribution network through SCADA and VAMs. It should also address power quality issues, and there should be reliable supply of energy. Networks should be self-healing with remote control switches and with a good outage management system, so that if some outage occurs, it can recover in the short duration, making it more resilient. There should be there is automatic customer billing. It consists of smart homes and buildings, and the consumers play a key role in smart distribution system. Now, smart distribution system architecture consists of smart meters, communication system, and management system and control schemes. This is the distribution system architecture for small and medium range uh, communication channel. The consumers have smart meters in their premises, and the local control center where we have the local data concentrator and the local control devices, and smart meters are communicating with consumers are communicating with this control center in bidirectional fashion through this communication channel, and then this local control center is connected to the main substation through another in bidirectional fashion through communication channel. For long range communication channels, it can be through satellite communication. The consumers have got smart meters at their premises and different number of consumers, and there is local control center. Both are interacting with the master controller at the substation through satellite communication system. Now, what are smart meters? Smart meters provide time-stamped measurement. Because that is the advantage this synchro phasor technology. At almost same time, unless all measurements are performed at the same time, then it will be of no use, because the voltage, current, all these are keep on changing. So if you perform measurement at some location at some time, and there is some time delay in measurement other location, so you cannot connect these two do computation at the same time, because system is highly dynamic. So voltage, current, all keep on changing. So we need time stand measurements, uh, that is provided by the smart metering schemes. Uh, this gives timestamp measurement, accurate measurements to customers, suppliers, and other market players for billing, control, and observation purposes. And they also smart meters store measure data for some definite period of time. And they also limit maximum power consumption. They intimate to the consumer that the power maximum limit consumption has reached. And smart meters also provide, it can be remotely controlled, it can be supply can be disabled and enabled through this smart metering scheme. And the smart meters have got bidirectional communication capability with control centers and other market players. And in case of theft and meter tampering, alerts and alarms can be generated at the control center. if somebody is trying to make steal electricity. Communication system, first smart meter component, smart meter, then the communication system, and then the third three components, then distribution management system. I talked about smart meters. Next, communication system. The features of communication systems are these are to be reliable. The data is to be secure. Should not be affected by weather conditions. And interference-free, tamper-proof communication, and cost-effective. And it should be robust against the cyber attack. Some cyber security should also be provided for this communication media. The communication system can be either wired through Ethernet and power line communication, or it may be wireless like Wi-Fi, GSM, WiMAX, Zigbee. Then come to the next what is third component is distribution management system and control. So control, we have one local, two controllers are there. One is a local controller. I have shown here. Say here, one is smart meter, local, say local controller maybe put at say a distribution transformer, and the master controller can be put at the main substation. So local control device functions may identify the phases, different phases, and also faulty phases, where is fault, and it can deal with the phase load balancing. It can protect the phases from overcurrent. It can disconnect the loads if there is some theft or something, and it can reconnect the load if there is overcurrent. Then it can also disconnect that consumer to protect the system, and again it can reconnect once something comes normal. It can prevent, but we should avoid shutdown of critical loads like hospitals, which are emergency loads. Should be able to detect power theft, detect meter tampering. Should be local controller should be able to identify the fault and remove and prevent loss of whole feeder. And it should be able to transfer the smart meter readings to main substation where we have master controller. Now, distributed generation play important role in smart grid, where we can locally supply in the form of microgrid or grid. The distributed generations consist of photovoltaics, wind generation system, biomass, etc. Energy storage system may be in the form of pumped storage hydro plants, flywheels, supercapacitors, magnetic energy storage system, battery energy storage system, fuel cells, and as per National Electricity Plan 2023 of Central Electricity Authority, the energy storage system will play an important role in the smart grid architecture. And also electric vehicles can also be helpful in the demand side management by its smart charging schemes. And it can also be able to regulate voltage and frequency. Now, energy storage system, as per National Electricity Plan 2023 of Central Electricity Authority, the energy storage requirement is projected to be around 2380 gigawatt hour by the 100 years of independence, 2047. What is the role of consumer in smart distribution system? The consumer becomes prosumer, able to produce as well as consume. We use pollution-free electric vehicles with smart charging facilities that I already told. We are able to control home appliances through remote control smartphones. We are able to shift loads from off-peak hours to through smart meters observation. Thus, the consumers play in the important role energy management system. They are also able to control their figures. So you see that consumers also take key part in demand side management. Now, this is some smart metering scheme. This is some paper work. This is some survey which are done by one of my PhD students. In the, they saw observed how these smart meters uh, improves the system performance. We visited Delhi and we see this with the smart meter readings, they are able to save the city billing. The difference in meter reading is shown for about 1 week for existing energy meter and smart meter readings. So energy consumption notice smart meter for 1 week was 28.024 kilowatt hour, or and for existing special energy meter it is 28 kilowatt hour. 28 kilowatt hour. So uh, you see the smart meter detects the higher energy consumption by small amount. So, but this is amount seems to be small for 1 week, but if you calculate for 365 days, then you can see how much revenue the utility is going to lose if the measurements were performed by the conventional existing special energy meters. No, this paper is based on the by one of my PhD student that he developed some architecture for a smart metering scheme in radial distribution network, and that he worked on monitoring, control, and protection of radial distribution network by a two-level control architecture where the local controller was put at distribution transformers and the master controller was put at the substation and the smart meters were put at the consumer premises. He considered the information flow in bidirectional fashion. Electricity flow, smart grid has electricity flow also in bidirection, should be bidirectional, but he considered in this his work only the unidirectional flow of electricity in his works. So functions performed by master controller was the load shedding and reconnection based on power available at the substation without disturbing critical loads. So he developed some the algorithm for load shedding reconnection that if power available power less than something, then you should disconnect some loads, and power available increases, then he should reconnect like that. He worked on that. Then functions performed by local controller were the phase load balancing, overcurrent protection of distributor, and theft detection. For phase load balancing, he developed some algorithm, calculated some average current, average of current difference between different lines, and also average of three currents. And based on that, he calculated this ratio, that is the phase current unbalance divided by average current. And if this phase unbalancing factor is greater than 10%, then he suggested to shift load from one phase to other phase to make the load balancing. So this was the algorithm. Similarly, he developed algorithm for overcurrent protection of feeders. So in the feeders, the currents were seen. What is the whether it is now how much is exceeding by the rated value, and if feeder current exceeding by certain percentage, then the loads are shifted from one phase to other phase, also to relieve that feeder, but that may create unbalancing also. So all this unbalancing algorithm and overcurrent protection algorithm, they have to be run. Both the algorithms are to run simultaneously in coordination. Then for theft detection, he developed the algorithm based on the readings of different meters, and naturally, if there is theft, that will not be measured. So he measured current at the control center. What is the current in that phase, and what is sum of current of different consumers. If that is matching, then it means there is no theft. It is not matching means somewhere there is theft. So based on that, he developed the algorithm, and the case studies were performed on this system. And it has 33 kV substation, and there was a master substation transformer, 5 MV, 33 kV or 6.6 kV. And he considered two distribution transformers where local controllers were put and master controller was put at substation. And he considered two areas, each area consisting of 21 loads. And then case studies were performed. These are different results. You see, for theft detection, somewhere alarm is generated in the MATLAB. This alarm was generated in the program. It is shown here. Then this paper is based on reconfiguration based by two of my PhD students, Lokesh and Achilles. They worked on the loss minimization and voltage stability enhancement under voltage dependent load. Reconfiguration was done using PSO CRO algorithm. So I told the reconfiguration, if loss reduces and voltage profile improves, voltage stability improves, so naturally the grid will become more resilient. So if somewhere there is the outage, the impact of outage will be less and the system can be restored at early stage. So reconfiguration is suggested this algorithm PSO-CR. They suggested PSO-CR algorithm, and they consider the different types of voltage dependent loads for study. The constant power load, the industrial load, agricultural load, residential load. Then also they consider the seasonal variations in load, the summer load, winter load. These are different. And the voltage dependent loads were considered this. The loads were modeled by this exponential model. The VD0, PD0 and QD0 are base gate load and the at rated voltage, and PDN, QDN are voltage at other loads power, real reactive power consumption by loads at other loads. And alpha beta are exponents that depends upon type of loads which are given in this table for different types of loads. Constant power, so it is independent of voltage, so it is alpha beta are 0. And for other type of loads, these factors are given. So he developed a multi-objective function. One objective function was power loss, which was given by this formula. This is based on old Algert's book, the exact loss formula. Alpha, beta are depend upon the voltages and the resistance, reactance of line. And this is P loss. Q loss, he has not considered minimization, but he has studied the impact in Q loss also. And these were constants which were considered the power balance equation, both real and reactive power balance equation, and voltages are to be within acceptable limits. The voltage constants were considered. In also the second radiality of the network is to be maintained. Radial nature of the network is to be maintained. That is the another constant. Then second objective function was voltage stability index, suggesting some of the paper he took, and then combined these two objective functions to formulate the multi-objective function. And this multi-objective function was optimized using PSO-CRO algorithm uh, to obtain the different reconfiguration in the network for different reconfiguration cases, and they found the optimal reconfiguration case for the network. The proposed algorithm was validated on this 33-bus radial distribution system, and for different types of loads. The system consists of 32 branches, 5 tie lines. Studies were performed for different types of loads. And the figure 1, optimal topology achieved by these switch changing, that is tie line switches, these 33, switch number 33, connecting bus 21 and 8, all these were uh, uh, closed and these were open to obtain the optimal configured network using PSO-CRO algorithm. Then these are different results: the power loss, the real power loss, reactive power loss, voltage deviation index, voltage stability index, and the minimum voltage at different buses. This is for base case. And this is for optimal configured case. So you see the electric vehicle load, this the P loss is minimum for optimal reconfigured case. It is 108.1092 kilowatt, and in the absence of reconfiguration is what 140.35 kilowatt. So this reduces significantly. Similarly, Q loss got down to 79 from 93. And similarly, minimum bus voltage is 0.92, and with reconfiguration, it got improved to 0.94. The voltage stability index 0.80 with EV, and without in the base case for EV load, it is 0.74. The index got improved. So this resulted in improvement in performance. So those things are written. Now, through bar chart, he tried to explain the base case reconfiguration is the blue one, and optimal reconfigured case is red one. You see the loss gets reduced for all types of voltage dependent loads considered. Then this is reactive power loss. In the multi-reactive function, he has not considered the reactive power loss in formulation of multi-reactive function. But this, since voltage stability index was considered, I think due to that, Q loss might have reduced with optimal reconfiguration. And for reconfigured case, the loss is less compared to base case for all the types of loads. Then this is the voltage stability index. You have higher voltage stability index means system is having more voltage stability. More voltage stability means more secure. More secure means more resilient and reliable. So optimally reconfigured case is having higher voltage stability index. So that is the conclusion that optimal reconfiguration improves the system behavior, performance. Then finally, the conclusion of my lecture is The resilient grid requires fast recovery of system following imminent disturbances, including natural disaster, extreme weather conditions, cyber attack, and the resiliency enhancement measures include design of equipments robust against robust against extreme weather conditions and disturbances and against cyber attack. And of course, if it is robust, then uh, it will be more secure, reliable as well. Integration of renewable resources, energy storage system helps in maintaining the grid resiliency and wide area monitoring system through Synco project technology helps in the real-time monitoring of health of system that will improve security, reliability, and better improve resiliency. So smart grid is incomplete without making distribution system smart, and a smart distribution system has bidirectional capacity and informations between supply and consumers. Smart distribution system consists distributed energy sources, microgrid, energy storage system, electric vehicles, and it has full automation through a smart metering scheme, SCADA and VAMs. The communication protocol should be either wired or wireless. The distribution system has a smart distribution system has architecture consists of smart metering and communication link and control center having data concentrator and control devices. Consumer play important role in demand side management smart distribution system and the reconfiguration of network helps in loss reduction, stability enhancement, and voltage profile improvement. Thus, it makes the grid more resilient, more reliable, more secure. And of course, grid is smart. Okay, so now your questions are welcome.
So now we are open for questions. Are there any questions from the audience?
I think one of the participants, Bhupendra Kumar, has raised his hand.
Yeah.
Bhupendra Kumar, do you have any question?
Yeah, what is question?
Are there any questions? Okay, sir. If not, this calls for conclusion of the session. Thank you, Professor MK Verma, sir. I would like to express our heartfelt gratitude for taking the time to speak at our session. Your insightful presentation and engaging delivery provided valuable perspective and greatly enriched the discussion. We truly appreciate your efforts in making this session informative and thought-provoking. Thank you, sir.
Okay.
Thank you very much, sir,
Yeah.
for giving your valuable time to our FDP. One of the participants has written some comment. He has Mr. NDV Prasad has written that thank you, sir, for very informative and clear explanation. So, on behalf of the organizing committee, we thank you, sir, for joining us.
So no query. I was expecting because faculty members are there. So
yeah, it is surprising.
And research scholar who are working.
So, anyways, if they do not have any query, so I request all participants that if in future they have any query, So they can pass the queries to us, and
So
we will pass the queries to Professor Verma.
That's why I made presentation my short, because I expected a lot of questions. Otherwise, I have discussed some more things.
Right, sir. Right, sir.
Yeah.
Right, sir.
Okay.
So if I think one of the participants raised a hand, but I think he by mistake he clicked on some button. So that's why his hand is raised.
Yeah. Okay. So I can quit now, no?
Yes, sir. Yes, sir. Thank you very much, sir, for joining us. Thank you.
Okay.
Thank you, sir. So we can end the meeting now. Thank you all for joining. And thank you, Khushbu.
Thank you, sir. Thank you.
Yeah, thank you, Khushbu, for coordinating the session.
Thank you, sir.